Good morning and welcome to the fifth and final day of the International Symposium on Information Theory. It's glad to see that many of you were able to make it up this morning after our late banquet last night. This morning I have the pleasure of introducing our plenary speaker, Professor Donald Geman. Don Geman had a somewhat unusual start compared to many of the people in this audience. He had his BA in English literature from the University of Illinois. He then went on to get his PhD in mathematics from Northwestern University. For 31 years, he was a professor of mathematics and statistics at the University of Massachusetts. His last position there was Distinguished University Professor. Since 2001, he's been in the Department of Mathematics and Statistics and in the Center for Imaging Science at Johns Hopkins University. Don has held many visiting positions. Presently, he spends approximately half his time at Geman, France, at ENS in the Centre de Mathématiques et leur Application. Don has given many invited talks and plenaries over the years and is a fellow of the Institute of Mathematical Sciences. I want to mention three items in particular. First, Don's 1984 paper with his brother Stu, entitled Stochastic Relaxation, Gibbs Distributions, and the Bayesian Restoration of Images, has been cited over 4,600 times. It's one of the most cited papers in our field. Second, Don gave a plenary talk at the Information Theory Workshop in Alexandria, Virginia in 1984. This was the workshop on information theory and statistics. So he has given plenaries to our group before, and it's time for him to return. Third, Don has been active in the Institute for Mathematics and its Applications Year in Imaging this past year, and in particular, he co-organized their week on visual learning and recognition in late May. And I had the pleasure of attending that week, and it was a very exciting week, and today we're going to learn about many of the topics that were covered that week. So, Don?
So you can hear me. Yeah, this thing is working. Good. Well, I'm really honored to be selected as one of your plenary speakers, and I thank the organizing committee for that honor. I'm going to talk about a topic which is probably relatively unfamiliar to most of you. I hope it won't just be new, but I hope it will also be engaging. It's image interpretation. Imaging, the intersection of imaging and information theory is not altogether new, and I'll come back to that. But the subject of image interpretation might be new to many of you. I'm going to begin by, at a kind of leisurely pace, telling you what the problem is, because most people are not familiar with it. And so I'm going to show you a lot of pictures to illustrate what the problem is. And then I'm going to discuss a few frameworks that have been proposed, both deceased and living, and even speculate just a little bit about an emerging theory or two. Then talk about, in general, a little bit hierarchical vision. There's a kind of consensus that hierarchies are perhaps the central structure of what we're looking for. And I'm going to conclude with a couple of mathematical results, which I think of as illustrating the efficiency of abstraction. I'll make that clear what I mean. So let's start with an orientation, a very gross orientation within imaging. I think it's sometimes convenient to divide imaging into three areas. Making pictures, so that would be the things you do in radiology and image reconstruction, PET and SAR and CAT scans and magnetic resonance and so forth and so on, how an image is made from the raw data, from the sensors to the image. And that's a whole field by itself. And then images to images, meaning problems like compression, restoration, enhancement, denoising, and so forth and so on. And then what I'm really interested in talking about here today is a third area, which is images to words. So the input is an image, and the output is a semantic interpretation of the image. And many of us who work in imaging feel that this is the grand challenge of imaging, is how do we interpret an image? Gee, did I do that? Okay. So, well, that's what I wanted to say, that computational vision, images to words, is, it's really an open problem. It's just, I'll illustrate very concretely the extent to which it's open. It's surprising to people how little computers, so to speak, can do, and how far behind natural vision they are. Now, I mean, it's not very shameful to be very far behind natural vision. Natural vision is utterly astonishing. You know, not only do computers, computers can't recognize, for example, faces or even detect them with extremely high accuracy. And we get on a bus and we see somebody sitting in front of us and it's nighttime, and from the back of their head we know who it is, right? So the gap between computer vision, between artificial vision and natural vision is really gigantic. So I'm going to assume just one grayscale image, generally there's massive local ambiguity, but less so globally, at least at the level of keywords. So some of the tasks that one is interested in is, find this clicker in an image, this specific one, find all clickers, or whatever these are. So that's the latter being generic object recognition. Find all instances of faces, find all instances of chairs. And you might want to do that simultaneously for many classes of objects. Human beings do it for on the order of 30,000 classes simultaneously. And you might even want to provide a semantic description at a somewhat higher level, like what's the global context? Describe the activities that are going on. That might be difficult from a single image. So here's a scene. And we might want to ask, is that a picture of Mao? That's object identification. So again, find my car, my suitcase. Is that a picture of Mao? Are there cars? Yes, there are cars, and a few of them have been circled. There are many other objects in this scene, and we might want to find all instances of all those other objects from a given repertoire of objects. We might want to categorize the scene very globally. So, a one or two word description of the upper left-hand scene is, I don't know, antique room. A one or two word description of this might be something like museum hallway. I think we'd all agree at that level of keywords it's a museum hallway. I think we'd all agree this is some sort of a gym and, I don't know, road race or something of this nature. So that's what I mean when I say that at the very high level of keywords, there's really not much ambiguity. So what are some of the things that make it difficult? Well, I could make a very long list, but I made a relatively short list of some of the things that make this problem so difficult for computers artificially. Well, one is clutter. There's a lot going on in that picture. There's a lot of stuff. I mean, if you had some list, find the faces and a few other things, there's a lot of other stuff in this picture. It's a more abstract example of clutter. There's an object, if you were finding people, there's a lot of other stuff there. Viewpoint variation, so I want to recognize this independently of the way it's positioned. I want to recognize it invariantly to both photometric and geometric transformations. It's still the same thing, right? I mean, there's a whole class of transformations under which the names of things stay the same. And obviously our vision system is invariant to those transformations. We'd like to design computer systems that are equally invariant. Lighting variation, that's the same person. And in any metric you can define between images, you will often have a situation where the same person under two different lighting conditions is farther, those two images are farther apart than two different people under perhaps similar conditions or whatever. Occlusion, so, you know, look at that horse in the middle. I mean, gee, we know that's a horse, don't we? Now, you could say if you took away these other horses, maybe you wouldn't, but you still might, and you certainly know that's a horse, and my God, how could you teach a computer to do something like that? Within class variation, so these are all boats, but they're awfully different from one another, but they're all boats. Those are all whatever they are. Every time I show this, I forget what to call them, but whatever they are, they're all the same. You know? How many samples do you need? This is a fascinating question, and this is why I'm going to assert a little bit later that a lot of statistical learning theory may not just be the right ticket for what we want. We recognize from really, it seems we recognize from a very small number of samples, those of us who have children have probably noticed that when you're teaching your child to recognize, let's say, the handwritten digit 3, you don't need a training set of size 100,000, do you? You know, you start showing the child 3s, and they get the idea pretty fast. It seems to be more like order 10 or something, rather than hundreds, thousands, tens of thousands, as would be used in most pattern recognition systems. So where do things stand? There's reasonable performance for several classes of semi-rigid objects. So if I said find chairs, tables, faces, and a few other things, you know, computer vision systems do a reasonable job. Now, even in the case of face detection, there's still a large, what we might call ROC gap with human vision. So take a scene like that. The object would be find the faces. Don't recognize the faces, just find the faces, all right? So what's the state of the art in computer vision? Roughly speaking, the state of the art, make a curve, a rock curve. So this is the false positives per image, and this is the detection rate. So up here you would be finding all the faces, and over here you would be doing a lot of hallucinating, right? You'd be finding faces in background, in clutter, in forests, in trees, and whatever. Then the state of the art in artificial systems is something like, if you're going to get 90% of the faces, this is over large standard reference test sets, if you're going to get 90% of the faces, find 90% of the faces, you're going to hallucinate about 1 time per image. That's sort of where everybody is. And if you're going to get, let's say, 95% of the faces, you're going to start to find faces all over the place that are not faces. See what I mean? And if you don't want to hallucinate, if you don't want to have false positive errors, if you want to have what's called high selectivity, I'm going to use selectivity in reference to the hallucination error, in reference to false positive error, and invariance in reference to detection rate. So if you want to be highly selective, you're going to compromise on invariance, i.e. you're going to miss real faces, all right? So that's where things are. Human vision is virtually perfect. Now, of course, it depends on the scale of the face, but it's virtually perfect. So as far as full-scale scene parsing, I said that was out of reach on the previous slide. Well, boy, I mean, there's a lot going on there. There's no computer vision system that can parse that scene and provide a rich semantic interpretation. That's the kitchen of one of the graduate students at Johns Hopkins, and there's a lot going on there too. I mean, you could have a list of object categories, and my gosh, that's tough. I once tried to explain this problem to, sometimes I just moves, but that's okay. I wanted to go here next anyway. I once tried to explain this problem. I was taking a French class. I'm going to tell you a brief story at the Alliance Française. And it was a conversational French class, and everybody was supposed to get up for 5 minutes and explain in 5 minutes in French what they did for a living. Those of us who, and some of the people were younger, they were students, whatever. So I had this great idea. So I made this little matrix. It was an 8x8 matrix with just ones and zeros. And it was very clearly a 4. You see, there were some ones going down and across and down, and all the others were 0. And I said, what I do is try to teach a computer to look at this 8x8 matrix and come out with the word 4. And people kind of looked at me, and somebody said, but it's obviously a 4. And I said, yeah, I know, we see it as a 4, but how would you recognize it's a 4 if the input was just these 64 numbers, zeros and ones? Somebody else said, but what are you talking about? That's just obviously a 4. I mean, what's the big deal? It was horrible. So here's the notation I'm going to use throughout the talk. I will be a grayscale image. Script Y will be a distinguished class of descriptions. For example, strings of class pose pairs. So the canonical example I have in mind is you have a list of object categories, like 10 categories, 3 categories, 1 category, faces, and you want to find instances from those object categories together with a rough pose. You know, where is the face, approximately what scale? Again, something for which there's in some sense ground truth. I'll come back to that in a moment. Now, I'm going to use Y for a hidden random variable that represents either one of the distinguished descriptions or other, which we can think of as background. And I'll use Y hat of I for the estimated, and it's going to be a set of descriptions. It's going to be a set. The estimator is going to be a set. And I'm going to use L for what people call a training set. Now, technically, if you had a joint distribution over images and interpretations, it would be an independent, identically distributed sample from the joint distribution. But in reality, it's just a set of pictures correctly labeled. Okay? So what would be the specs of our ideal description machine? Well, basically, there would be explicit instructions for doing everything, for designing it, for learning it from data, and for executing it online. And, ideally, you would not be allowed to say, well, the description I want is the minimum of this cost functional, some very, very difficult cost functional. You would have something much more explicit than that really executes things online, doesn't solve some intractable optimization problem. And ideally, there would be a supporting theory which guides construction and predicts performance, a theory behind it, a theory that achieves abstraction, but at the same time guides the development of practical algorithms. I mean, that's a tall order. There aren't many of those in the world for many subjects, right? Shannon provided essentially that for communications theory. But, one of the things I want to talk about, one of the key things is, do we have an analog for image interpretation? So what about ground truth? Well, this is just, you can just read over as I speak. This is just a kind of maybe formal way to say that if the set of descriptions is sufficiently simple, then I think most people agree there is ground truth. Like detecting the faces in an image of, let's say, some minimal size, as I said before. Finding the chairs and so forth and so on. There is ground truth. As soon as you get to a more complex level, obviously interpretations will differ. And people will have different levels of description and detail and so forth and so on. But at a very primitive level of keywords, there is ground truth. Okay, so that's the problem. That's the problem. And okay, I've managed to do that on time. So now what have people proposed for this problem? Well, okay, I'm going to say things that I'm going to go out on a limb a little bit and exaggerate, but I don't think it's a gross exaggeration to say that these are some examples I think of, in my view, and many people would agree with me, of some deceased frameworks, okay? So in the 60s, the AI community thought, okay, I mean, there was this famous story of a summer project at MIT where somebody, I can't remember whom, assigned to a class to solve a vision problem over the summer. Just come up with some rule-based method for interpreting natural scenes. And AI approaches were thrown at the problem, and I don't think they succeeded, and I think most people would agree they didn't succeed very well. The MAR paradigm dominated vision for a long time. The idea was it's a bottom-up procedure. We're going to start by finding like the edges, and then we're going to put edges together to make little longer segments, and then we're going to find whole boundaries, and then we're going to do something called that was the 2D sketch, and then there's going to be the 2.5D sketch, which brings surfaces and other quantities into the picture, and then eventually we're going to make a 3D reconstruction, and then recognition will be a byproduct of a faithful three-dimensional reconstruction of the scene. Now, of course, for that you would need multiple cameras or other information, but the basic idea was that recognition would be a byproduct of reconstruction, and reconstruction would be a stepwise bottom-up process, building up the scene, reconstructing the scene piece by piece. In the 90s, people were very excited about the idea that for any object, what you're going to look for are invariants, geometric and algebraic invariants. Find functionals which don't change regardless of let's say, the scale, position, and orientation. Find invariant functionals of objects. Search for those. One of the problems was that they involved, when they did exist, they involved high-order derivatives, second, third, fourth derivatives. And okay, computing first derivatives in a digital image is one thing, but computing a fourth derivative gets, in my view, kind of flaky. So here are three living frameworks that people are actively pursuing. So generative modeling is the stochastic approach. It says build a joint probability distribution over images and interpretations. And then typically, now you don't always have to do this, once you've built this joint distribution, and by the way, oops. Why did I lose this? Okay. By the way, the standard way to build it is to build a distribution on interpretations, sometimes called a prior distribution, and then build a distribution on the data conditional on the interpretation, sometimes called a forward model. People, this is all very familiar to people in speech recognition. Build a forward model, a data model, and then multiply the two together, and you've got the joint distribution. And then go through the Bayes formula, turn it around, and base inference on the posterior distribution. So this max is over interpretations. So choose the interpretation that's the most likely given the data. Now, if your prior distribution is the uniform distribution, then this is equivalent to maximum likelihood, right? So find the interpretation that is most likely given the data. Now, that's equivalent, some people like this way of expressing it, that's equivalent to minimizing overinterpretations minus logarithm of the data distribution plus minus logarithm of the prior, with the obvious interpretation that we're searching for the interpretation which minimizes the sum of two description lengths, the description length of the explanation and the description length of the data given the explanation. And some, particularly people naturally in information theory find that an attractive characterization of what other people call the map estimator. So there are many, many examples of these generative approaches. And I'm going to critique each one. And the critique here is that it's very elegant in conception, and some of the most successful systems indeed use this formalism, but it's pretty hard to pull off in practice. It's not so easy to design that prior distribution. Computing the map estimator, doing argmax is very difficult, very, very difficult. If the model is simple enough that you can compute the argmax, it's not going to capture the real-world correlation and the very rich dependency structure among the observable variables. As soon as you have a rich dependency structure among the observable variables, features of the image, or if you have a distribution directly on the image, then you're going to be in trouble when it comes time to compute the most likely explanation. So you're kind of caught either way. Either you have a kind of simplistic model and you don't capture real-world complexity, you make mistakes, but you can compute, or you have a kind of realistic model that captures real-world complexity, and then you can't compute. So discriminative learning. So this is machine learning. This is statistical learning. If Vapnik were here, he would say, oh, forget these models, P of I, Y. What do you have to do? You have to recognize this, and you have examples of this, so go from the examples to the decision boundary more directly. Forget going through a model. We're biased towards models. Those of us who are mathematicians, we love models, but who needs a model? Just go right from the data, in some sense, construct a decision boundary, because that's the problem you have to solve. Don't solve something harder than what you have to solve. Just directly construct decision boundaries, or almost directly. Well, the modern view is that basically you find the posterior distribution, but in its simplest form, you normally would replace the data by a feature vector. You would quantize the space of interpretations to a relatively small number of classes. You have to, for this approach to work. You would specify a family of what are called classifiers, and then you would induce one from the training data, L. So you would induce a member of this family from the training set. That's the recipe of statistical learning. And there are many, many examples, all the familiar examples, decision trees and support vector machines and nearest neighbor classifiers and so forth and so on, are all examples of discriminative learning. What's the critique? Well, in principle, universal learning machines that are going to learn everything from examples, right? So if I have enough examples, I'm going to learn about invariance, for example. I'm going to learn this is the same as this is the same as this, and change the lighting and so forth and so on. So in principle, universal learning machines. And there are solid foundations in statistical learning theory. The problem is that, as I indicated earlier, a lot of the interesting limit, at least if you want to close the ROC gap, the interesting limit is as the size of the training set goes down to 1, not up to infinity. So statistical learning, there are a lot of results in statistical learning theory about asymptotic results, about what you can do, but a small training set in some ways is much more satisfying than a gigantic training set. Now, if you just want to solve the problem, you could say, so what? So what if you have 1 million examples of handwritten digits? If you get the job done, well, okay. But there would be something nice about doing it with dozens or hundreds. And maybe even more seriously, I would assert, in practice, it lacks a global structure to address a very large number of classes. Let's say you don't have to be 30,000, how about 100 or 500 or 1,000? And small samples, the bias variance dilemma, which I won't talk about right now, and this invariance versus selectivity. What I'm trying to say is that it's too data-driven. It doesn't incorporate prior knowledge. And there's just too much to learn. Let me summarize it that way. There's just too much to learn. Now, there has been some effort to apply information theoretic ideas in imaging. And as an example, there was an issue of the IEEE transactions on information theory in the year 2000 dedicated to imaging. But you can't read that. Maybe you can, I can't. But if you could read the titles, you would see that most of the papers were in one of those first two areas of imaging I talked about. In fact, all of them, really. There is a paper here, for example, by Gray and others that talks about, has the word classification in the title. But it really means assigning arbitrary symbolic labels to pixels, the so-called segmentation problem. It's not at a semantic level. And so really none of the papers, except there's one about rate distortion for automatic target recognition that you don't see here. I think it was by Mike Miller, actually. But you know, by and large, all of this work was in sensors to images, images to images, not images to words. Now, there are two frameworks that people are in the process of developing. Song-Chung Zhu and colleagues at UCLA are doing something called information scaling. I'm not going to talk about that today. And Jody O'Sullivan and colleagues are developing something that they call information refinement, and you know, in a rate distortion framework, considering trade-offs between resources and complexity. Both of those at the moment are tilted more towards the theory rather than, you know, parsing scenes, and they're emerging. A colleague of mine made that up for the same meeting that Jody spoke about at IMA. We had one of the sessions was connections between information theory and imaging and high-level vision, image interpretation. And he just made up this chart to show where some of the tools of information theory have been applied in imaging. And it's mostly at the level of just taking tools, just thinking of concepts from information theory, you know, all variations on entropy and rate distortion and others, and using them as tools. I don't want to dwell on this. So overall critique of these, this is a critique of what I called the living frameworks, okay? They lack efficiency. There's really no global organizing principle for the vision problem. And there's certainly sparse theoretical support, at least for the practical systems. So for the face detection systems, for example, that exist, there's almost no theoretical support. So I come to hierarchical vision, which I believe is the right structure for vision, and I'm going to try to explain why I think it's the right structure for vision. So the basic idea is very simple. It can be illustrated here. Let's find shared properties of objects, and let's build up detection mechanisms and vision systems by exploiting shared properties and attributes. And I'm going to make the connection to information theory in just a minute. And we'll incorporate discriminative methods, information theoretic methods, generative methods as needed, but the core structure will be shared attributes. And I'm going to assert that this can yield efficient representation, processing, learning. Now, there's a lot of examples today of hierarchical vision systems. These are just some of them. I could have listed others. A lot of people are doing this kind of thing. I have a brother Stewart who's pushing a method they refers to as compositionality, and it's quite powerful. Shimon Ullman and his students are talking about hierarchies of fragments. Tommy Poggio, for years and years, has been developing a model that's faithful to what we know about processing in the brain, that's faithful to a true neural network in the sense that he tries to build it to be to reflect the different stages of processing in human brains or monkey brains. Jan LeCun's work on convolutional neural networks, hierarchical generative models, and so forth and so on. I'm not going to talk about all these. I'm going to talk about hierarchical testing. I think it's the one that in some ways comes closest to information theory, and it happens to be the one that I'm involved in myself. So I just want to say that as far as an emerging theory goes, I see more or less one candidate at the moment as far as a somewhat coherent, a theory that's at least off the ground, which is compositionality. It would be a whole separate talk. There are actually a couple of theoretical results. I keep aiming this wrong with this hand, which is very odd. There's a couple of theoretical results on efficient representation. It's a bit counting argument. And there are some theoretical results on selectivity. Remember, selectivity refers to false positive error, to high selectivity means you don't hallucinate. There are some results on selectivity in the context of likelihood ratios. But what is keeping the theory back a bit is, at a practical level, the contextual constraints which are employed are at the expense of learning and computation. It's very hard to compute with a compositional system, and nobody has any idea how to learn one. It's all handcrafted. We don't know how to learn it from examples. It's entirely hand-designed. So I want to talk about now hierarchical testing. So the idea is actually very familiar to anybody who's ever just looked at what a code is. So the idea is to course-define modeling of both the interpretations and the computational process. There's actually a lot of evidence in neural systems for extremely course-defined process. There are these almost shocking experiments of Thorpe and others that indicate that human beings recognize categories before instances. So you recognize that you're looking at it. If you're shown a picture very, very rapidly of an animal, you might know you have seen an animal before you know which animal you've seen. You might know you've seen a vehicle before you know you saw a truck. And I think that's perfectly natural, because I think that my own view is you have to look for everything at once. Vision ought to be course-defined. And so I said it's a shocking experiment because that's not what the psychologists and psychophysicists expected, but I think it's somewhat natural. So one byproduct of an approach like this is that if you're processing a scene like this, and you look at the density of work, the amount of time you spend processing the different regions, it will be extremely skewed because of the course-defined nature. You'll reject background areas very, very rapidly with very, very little computation. These are some of the people that have been involved with me in developing this approach to vision. One of them is here. And I want to say something about the way this developed, because historically, for me, the way this developed over the last 15 years or 18 years was really as I'm about to show you on these transparencies. So the first observation is very simple, and that is that one way to think of an ordinary garden variety code, this is just the simplest thing, is a code can be thought of as a course-defined exploration of the values of a random variable, right? I mean, that's what it is. It's just this link is often made, right? The link between coding and 20 questions. you're allowed in principle to ask any question of the form, is the value of the random variable belong to a set A, where A is an arbitrary subset of the values of the random variable. So, and all answers are exact, and Y is the only source of uncertainty. Okay, so I think that's irrefutable. That's what a simple code is. Now, that doesn't work. I mean, that paradigm, you can't just transport that to the vision problem and say, why don't you just build a code for the space of interpretations, assuming you had a distribution, for a lot of reasons. And this actually is going to make a connection with Alsveda's talk yesterday about Ulam's liar problem. There's a couple of problems. First, when we play 20 questions, we don't have all subset questions. We have questions that correspond to American, writer, dead, etc., right? So those are subsets. Those are specific subsets. They're attributes. So the first restriction is that we don't have all possible questions. We have selected subsets. But still, in the constrained 20-question scenario, just a binary matrix where you just imagine the columns are your tests and the rows are your hypotheses, and you have a binary matrix. If you go down a column, you see the results of a test for the different hypotheses. If you go across a row, you see the answers to all the tests for that hypothesis, for that value of the random variable. If you just assume the rows are distinct, right, then the tests determine, the questions determine the hypothesis. There is an optimal strategy. It's an NP-complete problem. So Y determines the set of tests and vice versa, and it's still an errorless unique path from the root to the leaf. Well, that's not going to do the job either for a couple of reasons. First, those tests are abstract. They're not realizable as image functionals, as measurements of the data. They're abstract quantities. And second, they have no error. They're exact. So one thing we have to do is make the random variables, make the tests realizable, make these questions realizable as random variables, as functions of the data. And that's going to require appearance-based shared properties. Is the first bit 1? What's going to be the analog of that in looking for faces? Another problem is that we have to accommodate mistakes. So here's the Renier, Ulam, I think it was Burkamp, liars problem. We have to accommodate mistakes. We're never going to build image functionals which are perfect, which will say yes on a certain subset of hypotheses if a member of that subset is present, and will say no if that subset of hypotheses is not present. It's never going to happen. So we have to accommodate mistakes. And the way we do it in this theory is we preserve one type of error. We assume that if the face is there, I'll give you a concrete example in a minute, that a test that might be designed for faces over a range of transformations will respond positively, automatically. And we pay for that on the other type of error, on the hallucination side, on the false positive side. And then finally, and equally importantly, we have to get away from a unique path from the root to the leaf. So we generalize from unique paths to what I'll call traces. Traces are labeled subtrees. You're going to go down many paths simultaneously. So the representation of the space of hypotheses, there's our natural groupings, and in fact, there are whole hierarchies of attributes. So this is a hierarchy of recursive partitioning of the space of hypotheses into, you take the space of hypotheses, you divide it into, you partition it, then you recursively partition, and so forth, all the way down to not exactly individual hypotheses, but we'll see in a moment. So if you were in an ideal world, and these were your 8 hypotheses outside of the background, here's a recursive partitioning of the space of hypotheses. Obviously, this first partitioning is based on color. This one is based on shape. Sometimes you continue, you just repeat the same set of hypotheses, because the test for this will actually be different than the test for this because of the alternative hypothesis will change. That's a detail. I'll come back to that later. But here are two examples of recursive partitionings of a space of hypotheses. Now, which one is another story? I'm not going to get into that. There's obviously a giant number of ways you could recursively partition a space of hypotheses, and I don't want to get into that today. So now what's the statistical structure? There's going to be a test or a question for each subset of hypotheses in this hierarchy, in this tree-structured hierarchy. Oops. And there's going to be a test for every one of these subsets. So there's two hierarchies here. There's a hierarchy of attributes, of sets, and there's a hierarchy of tests. And the overriding constraint is going to be that if the true interpretation belongs to AXC, the test dedicated to the subset AXC must say yes, and we'll pay for that on the side of the other type of error. So it's one approach to the Ulam-Liar problem. So here's a summary. It's very, very simple. There's a tree, just a tree, associated with every node of the tree, there's a subset of hypotheses. These are recursive partitionings, and associated with every node of the tree, with every one of these subsets, there's a test. These are not the answers to the test. They just lead to the next partition. The answers to the test are just yes or no. Yes, the hypothesis belongs to the subset. No, it doesn't. If the answer is no, you know it does not belong to that subset because of the constraint on false negative error. And then we're going to explore this under some strategy. And the set of interpretations that we keep, the result of our explanation, is going to be all interpretations that are not ruled out by any test. You can think of it as a complete path from the root to the leaf. And that constraint that I mentioned will imply that the true interpretation belongs to this subset, with probability approximately 1 if the false negative constraint is satisfied. Okay, so here's a very, very simple example. Here's a hierarchy. Here are, if you did all the tests, this is what you would observe. The only tests that survive are those that are hypotheses that, the only hypotheses that survive are those that are here or here. Here's what would happen if I process this thing by breadth first course-defined search. I would do this one first. The answer was positive. Since the answer is positive, I perform both of these tests. Since the answer to this one is negative, I can forget all of these, etc. So breadth first course-defined search is the natural search strategy in this framework. I'm going to skip this in practice just to say you build the tests using standard results from machine learning. You have positive and negative training examples, and you just build a test any way you wish. I'm going to have to skip the example. I'm running a little late, and I want to finish in the next few minutes. And so I'm going to skip the example that I was going to illustrate all this, which is a hierarchy for detecting faces. Basically, you just split on position, scale, and tilt. You have the pose spaces, all poses in the scene, and you just recursively partition the pose space, splitting individually on scale, tilt, or location. Here it is graphically illustrated. The faces that are at the top, these are all faces actually in a reference set of poses, and when you get down to the leaf cells, the faces are very constrained. So what you're going to do is you're going to ask questions at the beginning that have to respond positively to faces over a wide range of transformations, and then later on, the questions are much more dedicated. These are a couple of actual hierarchies that are built, and these are the kinds of results you get. And I want to skip this because I want to have just a few minutes left to talk about a little bit of theory. I kind of mismanaged my time a bit, but par for the course. It's real stuff. I mean, this has been applied to digits and tracking and license plates and face detection. It's a practical system. So why course-defined search? Let's suppose that I allowed you to execute any search strategy, whatever, of this sequence of this hierarchy of tests. You could just do the fine ones, that's template matching, the ones at the bottom. You could say, forget all this general tests, like forget all the first bits. Just go right for the hypothesis. Just ask the individual hypotheses one at a time. That's an allowable strategy. You could do those, and then you could do find a course. You could say, no, I want to do those, and then I want to go and do courser things, or I want to go course to find. I want to go in any order whatsoever. I want to visit the tests in any order whatsoever, and the cost of testing is going to be the sum of all the costs of the tests I perform, plus C star per remaining hypothesis, to do some dedicated, specialized test to just nail it. Is that really there? So that's the natural cost function. And you want to minimize this cost function over all possible strategies for visiting the tests in the hierarchy. And we proved a theorem. I'm going to skip the conditions. We proved a theorem that said course-defined search is optimal over all possible strategies if the ratio of the cost to the power, the cost to the selectivity at every node is smaller than the sum of those ratios at the children. If that condition is satisfied, you want to play a 20 questions game. You want to proceed course define. And it's close to necessary. We have examples where it's right on the edge. So course define, breadth first course define search. Do the courses test. If the answer is no, you're all done, and the set y hat is empty. If the answer is yes and you were to stop, the set y hat would be all hypotheses. If you continue with course define search, do the two children, and in general, perform a test if and only if all its parents' ancestors have been performed, all the courser tests have been performed, and returned a positive answer. That's the optimal search strategy under this condition. And so in the world of 20 questions, what you're saying is do something very natural, right? Start with tests which have broad scope but relatively low selectivity, just as you do when you build a code. And proceed successively, ending with tests that have narrow scope because they're dedicated to specific hypotheses, but they have higher selectivity. Naturally, they're going to have higher selectivity at a given cost because they have an easier problem to solve. And bring cost into the picture. And since course-defined search is optimal, and by the way, the conditions that I jumped right over are somewhat natural, not entirely realistic, and we'd like to extend the theorem to more realistic statistical assumptions, but if the conditions are satisfied, we know course-defined search is optimal, and hence we know when we perform a test, we know what the right alternative hypothesis is. The right alternative hypothesis are all the images that have reached your parent. Because you're only going to perform a test if all the ancestor tests have been performed and are positive. So we know what the negative training sample should be for testing the hypothesis Y belongs to A. It should be all instances that satisfy all the courser tests in the branch between you and the root. Okay, I think I'm going to have to skip this, unfortunately. It's the trace model. It's a probability distribution on the history of processing. That's where we put the probability distributions, on the history of processing, which we call the trace, which is a labeled subtree. So there's a tree hierarchy, there's the results of the tests. That's the subtree you processed, and that's the subtree you processed together with the test results. And the probability distribution is on the history of processing, which is not a unique path, root to leaf, as it is in a code. It's a whole labeled subtree. And you put a probability distribution on traces, and course-defined search can finally be thought of as an exact implementation of a likelihood ratio test based on the trace distribution. That's kind of the bottom line. Course-defined search is an exact successive approximation to the likelihood ratio test where the object that you're building distributions on is the set of histories of processing. Now, I had to compact this. I apologize for that. I had to compact this trace business, and it might have been, because it's a kind of generalization of an ordinary code, it may be something I should have reserved more time for. I'm sorry for that, but I think you get roughly the idea. Let me finish up. This is about improvements you get with this trace distribution. So conclusions. Hierarchical testing. I think it can be seen as an adaptation of source coding to vision. It hardwires invariance and computational efficiency. It is limited by an impoverished contextual analysis, something that compositionality supplies, but at the limit, at the expense of efficiency. And my own current view of the vision problem is a lot of it has to be done online. I think that we actually do something like hierarchical testing to throw out plausible interpretations. Some people call it indexing. And then only then do we know the classes we want to build a classifier for. You learn the classes online, and then you build dedicated procedures to resolve the ambiguities you actually encounter. I just learned from Sanjeev Kudanpur that my colleague Fred Jelinek is doing something very similar in the area of language processing that he calls code breaking. And here are some final conclusions. Just take-home messages. There is a dramatic ROC gap with natural vision. In my view, there's no Shannon in our subject of image interpretation. Nobody has come along with a theory of image interpretation. I think all the ambitious proposals center on hierarchical structures. I have my own favorites. I talked briefly about them. Others have other representations. But so far, none is simultaneously efficient and contextual, and I know I glossed over what I mean by contextual, and there's very little supporting theory. I'll stop there. Thank you.
Thank you very much, Don, for a stimulating overview of this area. I think in the interest of time, we're going to skip questions, but Don will be here for the rest of the day, and please talk to him later.